All right. Now, there's been a lot of people away. Guys, this booklet we made up last year to prepare you for the SIS test, which is going to be in week 1 of term 3. And it also because previous WACE exam questions have had error bars in them. All right. And we're going to go through a couple of examples today. And then I'd like you to complete this booklet over the holidays to prepare you for the SIS test. Okay. So we'll go for about maybe 30 minutes and then I'll give you back your tests. But let's just recall, this isn't in your booklet because I've only just added this last minute. It will be on the OneNote. We looked at error bars when we did this little quick demo of determining the magnetic field by varying the current through a current carrying conductor, measuring the force. And then I, at the last minute, decided to add an absolute error bar. So we got to this bit. Now, I just thought I would add here, after the fact, I decided to add error bars. And obviously, without the error bars, the data ranges from 0 to 4. You need to be careful if you ever have to plot error bars. You've got to make sure that they lie on the grid. So in this example, I probably should have gone from -1 up to 5. And that way your error bars lie on the graph paper. So again, this would have probably gotten 4 out of 5 or 5 out of 6. If this was a response to an exam question, you'd be losing a mark there, okay? Now, here's where this method has appeared in, I'll show you some examples, but we looked at this that obviously you can get your line of best fit where you try and get them all to line up, least squares regression. But then you can take from the bottom of the first error bar to the top of the last would give you the maximum allowable gradient with the error, and then vice versa, from the top of the first through to the bottom, that would give you the lowest allowed gradient. And here, we did this earlier in term 2. Across the page, we rearranged to get the magnetic field strength as 165 millitesla. But however, the minimum gave us down to 120, and then the maximum gave us up to 195. Yes. Now, the way to determine your error from that is simply to take half of the range. All right, and this has been shown in previous exams, and we'll go through an example in today's lesson. So the range was 75, and so half of the range gave plus or minus 37.5. One little quick refresher. However, remember, gents, you need to express your error in the same decimal places as your measurement. And there's obviously a little bit of variance as to how this is taught. I would like you to, when taking gradients, these are estimates. Brendan, can you close it, please? No, you're not. These are estimates, and generally they'll be to 2 significant figures. But obviously, in all the different schools, some students are still providing them to 3 sig fig. So when gradients are appearing in WACE exams, they will allow 2 sig fig or 3 sig fig. I'll talk more about that later. However, if we looked at expressing it as in Tesla, 0.17 plus or minus 0.04, we had to round that value so that it was to 2 decimal places. The problem here, if you go 170 millitesla, then it's no longer decimal place, it's now to the nearest 10. So 170 to the nearest 10. It's difficult to show that. I reckon scientific notation would be your friend at that point. If you went 3 sig fig, then that's fine, 0 decimal place, and we can round your error to 0 decimal place. If you ever got a measurement that had to be rounded to the nearest 10, as I said, scientific notation would be your friend. You would go 1.70 plus or minus 0.40, all being multiplied by 10 to the -2 Tesla, or millitesla. Okay, so that's how you would get around that. Now we've got decimals because I've just added an order of magnitude. Okay? All right, so that's just a quick little refresher on our first kind of look at gradients earlier this term. So guys, let's just quickly look at a 2012 exam question that appeared. This was just a copper rod traveling down a magnetic incline Obviously, it reached a terminal speed where the backwards repulsive force of induced magnetic fields equaled the forwards, blah, blah, blah. They determined the relationship. Here is our graph. Now, let's just have a quick look at what's going on here. We've got the sine theta of the angle of the incline. Changing the angle changes the sine theta. And then they're measuring the terminal velocity in centimeters per second. Now, here we've got error bars on both axes. So both measurements came with an associated error. Let's just look at the sine of the theta. We start off with one line is 0.02, and we start with a large error, and then as the sine theta, the absolute error decreases. Okay? So it may be, I don't know how they were measuring it, but the absolute error appeared to decrease as the sine theta increased. Looking at terminal speed, obviously something different. You have a low absolute error, and as terminal speed increases, the absolute error increases. Now have a look. The question number D, 4 marks. All you had to write is pretty much what I said. As sine theta increases, the absolute error of sine theta increases, and that was worth 2 marks. And then as the terminal velocity increases, the absolute uncertainty of the terminal velocity decreases. 2 marks. So 4 marks, 4 minutes of the exam, you could get that written down. Well, you have a quick little scowl of the data. It would probably take you 2 minutes. So this was an example where this was way over marked. Okay? This would be a question you could do quickly, and you could save yourself a couple of minutes elsewhere. Okay? I will place the solutions up later on in the holidays. I want you guys to obviously have an attempt first. Let's just have a look at the first question. Express the value in that form, where y is the terminal speed and delta y. Okay, so they just want you to go up here. Now, again, be careful that central dot is just below. I'm going to draw it again, just below. This line here is going to be 0.04 of a scale step. So it's 0.84, but it's about a quarter back. So I reckon it's about 0.83. So I would say your V equals 0.83 plus or minus. And then we're going to look at the size of our error bar. So remember we said that each of those semi-minor grid lines are 0.04. And it looks like we're about the length of a semi-minor grid line. We've just been shifted down a bit. So I reckon the error is pretty much one of those semi-minor grid lines, which is your plus or minus 0.04. So back over the page. And conveniently, the error is being expressed correctly to 2 decimal places because our measurement was given to 2 decimal places. Okay, so it's testing a fair amount there. Now, I will leave you... this one. When drawing the line of best fit, the students chose not to include the 2 largest terminal speed measurements because they thought they were less reliable. Let's just have a look. So you're going back to drawing your line of best fit because that's what you have to do for the later questions. And we kind of want, obviously, we've got now. Here's, if you got 2-axis error bars, what this is saying is that this dot point that I'm highlighting could really be anywhere inside this rectangle, and the size of the rectangle is determined by the vertical and horizontal error bars. All right. So instead of it being sliding up or down, it could be anywhere in that square. Okay. So now when you're drawing your line of best fit, you could omit a dot point if that box is not on the line. All right, so for example, if there was a dot point here, for example, then obviously all the others appear to line up. All of the error bars line up except for that one. I would treat that as an outlier. It would be a random error. Something went wrong with the measurement of that data point, whether it was distance, time, angle, length, atmospheric pressure, temperature, Alex bumped the table, the stopwatch fell over, random error, okay, that we cannot calibrate for, okay? But it's asking about the last 2 points. And the reason is, if you look at the last 2 points, let me just get rid of, no, it's not going to let me. Is it going to let me? If we look at the last 2, their boxes actually overlap. In fact, all of the boxes overlap. But if we look at the edge of our data, this brings us a problem. And the problem is that this data point could be up here, and then this data point could be down here, which means our data could actually curve downwards. We don't have any outside data point to show us that it's on a line. If there was another dot point up here, and then you go, well, it's not going to do that. It's actually going to do that. All right. But because it's at the edge, we don't know. So if we choose to eliminate those last 2, we could say, well, it's definitely linear up to these points. But these 2 we're not too sure about. Now, if you were doing this experiment, what could you do if you wanted to go back and correct for this or include them? What could you do? Take another measurement. Go to sine of 0.9. Go to sine of 1. That would be vertical. And then if those ones line up, then we're good. All right. So the marking key actually said the error bars overlap. Hang on. So the value of the sine of 0.82 lies within the uncertainty range of the terminal velocity of 0.87. So we're saying that the uncertainties overlap. Without further measurement, it's difficult to determine whether the line is curving at the top. But then the marking key also says, using a good experimental justification, allow 1 to 2 marks. So the markers are right. Well, if a kid gives a good justification, give them the mark. Yes, Ed, what is it?
The same being said about the first 2 points as well?
Possibly. No, because the boxes don't overlap. So the boxes here are like that. But I mean, could it be doing that? Possibly, yeah. But obviously, guys, this uncertainty, this unknowing is going to occur for every outside range. Your lowest value and your highest value is going to be at the edge of the data, and you're not sure unless you just continue more data. So you've always got that unknowing of your outside 2 values. Now, drawing your line of best fit, we said this explicitly to the year 11s, that no effort should be made to draw your line of best fit through the origin. Even though the equation on the next page is telling us that there should be no y-intercept, no effort should be made. And generally, you draw your line of best fit until it hits an axis. So I should have just, there we go, until it hits an axis, and then you stop. If you are collapsing your axes, then you do not extend your line of best fit beyond the collapse. Because obviously, if you've just truncated your axis, then there's no way to express that pattern because you've changed the scale. So just be careful with that. Other things. Remember that you should be choosing for your gradient a point on the line and not a point given. I mean, it might be convenient that they appear on the line, but again, use the line of best fit, and generally we ask that your triangle should be at least, a good size of the page. Gets a problem though when we get to minimum and maximum gradients as well as the line of best fit gradient. You're going to have a lot of work going on. In the example we're doing today, I don't draw my triangle, I'm just going to draw my coordinates. Okay, and sometimes you can use the same coordinate. I'll show you as we get to it. Yes, Mahone?
We would always have to draw multiple triangles to calculate, we get in trouble if we write the coordinates. I'm
always a bottom right kind of guy, but I know a lot of people go top left, so you could always draw your triangle top left. Yeah? I know, right? Ideas, man. A whole new world. Okay? Alright, so, just before we go on, obviously the reason we give you guys data is that you might want to linearize it. We've got this in the form V equals something times sine theta. That's your y equals mx. So we need to get sine theta out on its own. So that's V equals mg r on L squared B squared times sine theta. So gradient equals that. All right. So I will leave you to determine you know, you've been given M, you've been given G, you've been given L, you've been given R, I think.
Yes.
Yes? Yes, cool, resistance. Solve. Now, just thinking, we've got centimeters per second on the y-axis. Sine theta doesn't have any units, so our gradient would be centimeters per second. Ohms, amps, volts, joules, Tesla, kilograms. I wouldn't even want to go near my buddy dimensional analysis for this one, but really, the gradient should spit out meters per second. Oh, also, SI units, so we want kilograms, we want meters, because I reckon gradient of that will give us meters per second. That would be an extension for any kid that wants to go home and try it out. Show that through dimensional analysis that all of that gives ms-1. But I'm not going to, because we're running out of time. Let's get over to this question. Now, a kind student has since given me the digital PDF. This was a scanned image, so I apologise that it's a little bit messy. This is going to make this activity a little bit tricky. This was 2 years ago, all right? 2 years ago, kids were given this, and you've got to do the maximum and minimum gradient. So if a kid had never experienced maximum and minimum gradients through error bars, they were not screwed, but they were screwed. They weren't going to get 4 marks. I'll go. Now, here's the thing. We've got this equation that we're familiar with. It's called the Biot-Savart law. Thank you, Ben Davison-Petch. I forgot the name of the law. We've played with that. That's the strength of a field dependent on current and distance from. Okay. Now, in this scenario, R was left as a meter. That's nice, that's just 1. And then they varied the current through the wire and they measured the strength of the field. So there's our graph. Now it turns out, this was, look, let me get real with you for a second. This wasn't the greatest question. Because this mu value here is actually the combined magnetic permeability of both a vacuum and aluminium. Turns out, in most cases, we do stuff in air, and air is so close to a vacuum that we just treat it as mu naught. But it can also travel through materials. And so if it has to travel through a material, then the total magnetic permeability is simply the product of the two substances, the vacuum times that. But you didn't need to know that. You were given the equation, and you saw how we might be able to extract the values. So if I said B equals mu on 2 pi r times I. Oh, look, there's my gradient. Yeah? So that's what the gradient represents. And also it's suggesting that there shouldn't be any y-intercept. So you would find the gradient, and then I reckon we would multiply it by 2 pi r to determine the magnetic permeability. Okay? And that's what we need to do. So let's get going. So I've got my... Now, 3 marks, 3 minutes. So you've got to find the gradient. So I'm going to do that. You do it as well. Pick a nice point on that line. Oh gosh, I'm going to go. Oh gosh. 0. Find a point. Time is. There's a point there. I'm going to go now. What are our scale steps? 1, 2, 3, 4. Point, oh gosh. So that is 4, 8, so that's 15.6, comma 1, 2, so that's 2 up, 0.0074. There's a nice one there. That's 10.4, comma. Going straight. Oh, that's on the 5 line. All right, 0.005. Come on, guys. I need you to be at the same pace as me, please. So pick your points. Please write the full equation down. Y2 take Y1. Okay. Now Y values. What was that? 15.6 take. Zero point zero zero seven four take 0.005 bracket 15.6 take 4.62 is what I get. 4.62 by 10 to the negative 4. The units would be Tesla per amp. All right, 3 minutes. All right, that's all the time that you should be given.
So what did you get, sir?
I got 4.62. Now, the waste marking key gives allow 4.76, allow as low as 4.54 and up to 5.01. Basically, they've taken the values and chucked it into a spreadsheet. Guys, listening please. They've added 5% and dropped 5%. So the actual value should be 4.76, but they will allow 5% up and 5% below. And that's what we tend to do when we do gradient questions. That's your allowed range based on how well you can get values off the table. Now, let's just go back. I estimated, this is an analog scale, all right? And you are allowed to estimate to 1 degree of precision higher on an analog scale. So if I went 10.4, I've got a 3 sig fig value. 15.6, a 3 sig fig value. But look at the y-axis. It's 1 sig fig. So all of my estimates to 1 degree higher is 2 sig fig. So that's why we generally, sometimes if you've got a precise scale, your gradient can be more precise. This example, I'm limited to 2 sig fig. But they didn't take marks off if a kid left it as 3 sig fig, even though these numbers here were 2 sig fig. So I'm going to just express mine, if you don't mind, as 4.6 times 10 to the negative 4 Teslas per amp. Okay? All right. Is everyone up to this point? Oh, hang on. We haven't, no, we're not done. Sorry. So gradient equals mu over 2 pi r. Therefore, mu equals gradient times 2 pi r. 4.6 times 2 pi by 1. So I've got to times my answer. 4.6 times 2 pi. Sorry, I'm waiting. 2.89 by 10 to the negative 3 Tesla meters per amp. Now, why did that meter suddenly appear? Go ahead.
R value.
Good, because of the R value. Very good. See, they made R a 1, which is a really nice number, but it tricked a lot of kids because they just multiplied by 2 pi. They're like, oh, I can simplify that out, and they just wrote 2 pi. And then when they look at the units, they forgot that R was present. So again, Tesla meters per amp. 2.89, marking key says 2.99, allow as low as 2.85 and as high as 3.15. Again, it's plus or minus 5% of the accepted value. Now, here's where stuff gets tricky. Next page, gentlemen, have a look. This is very poorly worded. This is my opinion and does not reflect that of the School Curriculum Standards Authority. Use the gradient and the vertical error bars on page 14 to comment on the uncertainty of your answer to part A. Use the gradient, find the uncertainty. All right? So, maximum and minimum. Now, 4 marks. I'm going to time myself. I read the question. Stopwatch out. Let's see how long it takes. It's going to be more than 4 minutes. That's why I don't like the marking allocation. So we get our rulers out. I'm going to color code this. We go from the bottom of the first error bar to the top of the last, and all of the intermediate error bars seem to be in that, so we're good there.
What happens if they're not?
Well, you could highlight it as an outlier,
Okay.
or move your ruler so that they are. Then I'm going to go a different color. Okay. Get rid of the ruler. Now, oh, that last, I'm going to try my line of best fit again. try that again. And then again, you've just got to find nice dot points, nice whole numbers. I'm going to go that one, which is 4, 8. Oh, that's 12, 4, 8. That's 10. Sweet. Oh, that's 1. Oh, that's cool. That dot point there is nice. I mean, you could be cheeky and just pick the top of the first error bar as your coordinate and the bottom of your last error bar as your coordinate, providing your line goes from there to there. You could just choose it. I sort of didn't do that, unfortunately, so I've got to pick somewhere else. 15.2, comma, 6.6. And then this one here was 1, 0.001, x and y's. Oh, that's nice. The first one is actually 1, 0. If you choose that first error bar, its coordinates are quite nice, x and y. But everywhere else is a little bit nastier. 15.2, comma, all the way to the top, 0.008. All right. So we'll go M max and M min, and we'll just start throwing everything in. What were our y values? 0.008, take 0. And that was 15.2 and 1. $5.63. So again, that looks good. My maximum is above my line of best fit gradient, so that confirms that I've got the right values. And now my Y2, that's going to be 6.6. No, it's not. It's not 6.6. Why did I write 6.6? That's 0.0066. 0.0066. And then 15.2 over 1. No. But this is how we're getting the absolute error. Well, yes, we will. We have to times by 2 pi r, yes. But I think you've still got more to do. 3.94. All right, now I'm just going. I understand some of you are still working. Again, my minimum is about 15% below. My maximum is about 15 to 20% above. So I know that I'm sort of probably got the right values. Now here's where we could go. You could find the gradient range and then multiply by 2 pi r, or you could multiply both by 2 pi r. That would give you your permeability range. You could then take the permeability range and divide by 2. It makes no difference. What did the marking key do? They found the range of the gradient and then divided by 2 pi r. So I'm going to do that. So my range, my uncertainty is going to be 5.63, take 3.94 over 2. gives 0.845 plus or minus 0.845. So that was, my gradient is now 4.6 plus or minus 0.8. All right, that's what we got to. But we want the mu naught value down here. So I'm going to go mu equals, we're going to go 2.89. No, we're not. No, we're not. Let's just go the absolute uncertainty of mu naught is going to be 0.845 times 2 pi r. 5.31 times 10 to the negative 3. All right, we're nearly there. From the previous page, I determined my mu value to be 4.6 by 10 to the negative... Oh, that value should have been smaller. 4.6 by 10 to the negative 4. But now I need to express him in the same order of decimal places. So that was to the negative 5. I could write that as 0.531 by 10 to the negative 4. I need to now round it to one decimal. So that's going to be 0.5 times 10 to the negative 4. Mr. Murray has finished the question. Stop the clock, 7.5 minutes. For a question that is only worth 4 marks. Uh-oh, what's up? Oh, I forgot my order. I forgot my order of magnitude, if that's what you were going to ask.
I think you use your gradient.
No units required. Yeah, I needed to find the uncertainty of part A, which was him. Oh, sorry. Gotcha. Oh, crap. So I got the whole thing wrong. 2.89. So it's 2.89. Oh, that should be 4. Okay. Sorry. 2.89 by 10 to the negative 3 plus or minus 0.5 by 10 to the negative 3. Sorry. I wouldn't even have picked that, and I would have lost a mark probably. So guys, let's just have a look at all of this. Damn, I was hoping I could get there. I don't like expressing that order of magnitude. I would have liked to have written it as 2... Oh, hang on.
Why is it 2.89?
2.9, thank you very much.
Wait, why is that, sir?
2.9. Because when I found that gradient on the first page, it was 2 sig fig. Okay? So, here's what we could have done. A student could have written 2.89 times 10 to the negative 3 plus or minus 0.53 times 10 to the negative 3. That's also fine. So they would allow 3 sig fig. They're not going to penalise significant figures in this question. Just hold. Because it's... Well, hold on. I would have preferred... If you have a common order of magnitude to place it outside the brackets, but then they went and stuck the plus or minus there, so you can't really do that. So you just have to include your order of magnitude. Now, Mark and Key said 3.0 plus or minus 0.6. Well, you're allowed a tolerance, so as low as 2.8 and as high as 3.2. I vividly remember marking this question because it was horrible. Horribly worded. Oh, next thing. The mark is, if I am in a markers group for WACE, I'm not supposed to say that I am in a markers group for the WACE. But there's something that I haven't done in this question. Have a look. Comment. Comment on the uncertainty. It's got 2 numbers with a dot in the middle. Done. I've commented on the uncertainty. The uncertainty is 0.5. Comment on is not a very good actioning word. So we like you to explain, calculate, justify, making reference to. Comment on is not a very good word. So the markers obviously decided that ignore that word comment. You're really looking for them to do maximum gradient, minimum gradient, find the range, multiply by 2 pi, put the answer in. All of that worth 4 marks. If this was a test, if this was a question done here, I would be going probably 2 marks, 2 marks, 1, 1. You're looking at least 6 marks. And with that mark, you'd have to also show you're working on the graph. You'd have to show your coordinates and your triangle. Okay? So a lot of work, students were spending 8, 10, 15 minutes on something that was only worth 4. Okay? So it may occur again, and I wish that it doesn't, that a question appears that is a bad time economy. Okay, and we looked at an example at the start where that 4-mark question on the sine, theta, and centimetres per second, you could get that out in under 2 minutes. You've just freed up 2 minutes to spend somewhere else. All right. The problem is when you're scouring in the reading section, in the 10 minutes reading time, I would go WTF. Nah, I'm going to leave that. I'm just going to look at every other question, and if I can finish the exam and have 10 minutes left, maybe I'll come back. Okay? So when you're scanning the WACE exam, don't look for the question that's going to upset you and get you in a panic attack. Oh, I'm going to do that one first. No. You go, you know what? I don't have time. I'm not going to look at this one right now. I'm just going to make a reference that I'm going to skip that question. Okay? To the end. Don't just skip it completely. To the end. I might be able to do... Oh, I can do part A. I know exactly what I need to do in part A, but what the hell is part B? Yeah. All right, so don't do it. Do it later. Do it at the end. So, guys, here was the problem. Next, this question... Shh. The way that the WACE exam is marked is not that the WACE marker sits down with Cameron Garside's test and marks it in its entire, oh, that's Cameron Garside, he's making these silly mistakes. No, you mark pretty much one page 180 times. Okay? So you don't know who the kids are. And if they make a mistake in sig figs and you take a mark off, if that's how it was done, then that kid might lose. If he hasn't been taught 3 sig fig or scouring the values for significant figures, he might and there are no half marks in WACE. You might lose 20 marks in a whole test for sig figs. And it did occur. So the WACE said, all right, maybe we'll pick a certain number of questions where we are assessing sig figs, and if they don't do it, then we take a mark off. This question was one of those. So you might see in the past few years' WACE exams that some of the questions will say, expressed to the correct number of sig figs, or to the appropriate number, or express your answer to 4 sig fig. That's the question where you could lose a mark if you don't do it. But then, this question was a bad question because some kids were going, all right, the gradient that I've chosen has 3 sig figs, so I'm going to follow through with 3 sig figs. But then other kids were going, oh, hang on, it's 2 sig fig. You know, so 2 or 3, but definitely not 4 or 1. That's most kids were getting this. Most kids were not losing marks for sig figs in this question. Yes, Robert?
So how many sig figs is the gradient?
Well, mine was 2. And I have already spoken as to why, but I will say it again. When I took my y values, that was 7.4. I'm allowed to estimate to 1 scale of precision higher. All right, so the scale there is obviously, well, you could argue, am I gonna guess that dot to 3 sig fig? Hell no. It's 7.4. I can't say it's 7.41. It's 7.4. It's 2 sig fig. So I'm limiting my precision to how well I know the value of that line at that point. I have spoken for too long, but hey, thanks for coming along. I'm going to hand out your tests now.